All right, good morning, and we are going to start pretty quickly today. Hold on, let me refresh this. Okay, so many of my softwares actually got updated. So if you encounter any issue regarding audio or video quality or anything related to the streaming, yeah, please let me know during the stream. All right, so we have been talking about transient response of systems for quite some time. We started our discussion with first order systems, then we jumped to second order systems, right? And today we are going to end our discussion on transient response with some more discussion on second order systems, right? So this is part 14 of our overall classes, and this is part 3 on the transient response of second order systems, discussion on transient response of second order systems. Now if you recall, this was our generalized form in which we were talking about second order systems, right? So we considered systems that do not have any do not have any zeros, finite zeros, but they do have two poles, and the location of the poles would be determined by the damping ratio and the undamped natural frequency. Okay, all right, so that is something we discussed earlier, and with that we also calculated the step response so of undamped and underdamped systems. Under undamped situation, when zeta was equal to 0, right? So we calculated the pole locations, and here were the poles. We noticed that the poles were on the j omega axis, rather the imaginary axis of the S-plane, right? And when we calculated the step response after doing elaborate calculations, we saw that the step response was an oscillatory response, okay, and the frequency of oscillation was equal to the undamped natural frequency omega n. Then we tried to find out similarity between these and standard second order systems, okay, in both mechanical and electrical domain, and we are going to look into standard systems in many other domains and also some other systems as well. We're going to look through those during our course, but before that we are going to gather a bit of more analytical knowledge here. All right, and then we considered the other situation where zeta was between 0 and 1 strictly. This was called the underdamped situation, right? And we also calculated the step response, but before calculating the step response, let's notice that on the S plane, this is again the complex plane, if we place the poles and zeros, you will see that they are a complex conjugate pairs, and they are on the left half of the j omega axis, right? Left half of the vertical axis here. So this is something called the left half plane, and we're going to again discuss everything. Just keep in mind, so this is again a complex conjugate pole pair, but they are no longer on the j omega axis, but now they are on the left half plane, right? All right, so again we calculated the response, and after calculating the response, we saw that the response was sort of an oscillatory, but the oscillation was dying down. Okay, the response was kind of oscillatory, but the oscillation would die down depending on the value of zeta. So if we have a higher value of zeta, then the oscillation would die down pretty quickly, but if I have a smaller value of zeta, then the oscillation would die down slowly. Okay, and similarly if we have smaller values of zeta, then the peak overshoot will be higher, etc., like that. Okay, and we calculated a few characteristic features, okay, namely the rise time, peak overshoot, and settling time. We had elaborate discussion on everything, but so far you have to understand that we have only considered values of zeta to be between 0 and 1. Okay, we haven't even considered the value of zeta to be equal to 1, right? We have considered values of zeta equal to 0, but and then so that was the undamped situation, and then we considered the underdamped situations when zeta is strictly between 0 and 1, not equal to 1 or not equal to 0, right? Now Again, we did these things, we derived all the expressions and everything in our earlier classes, and we solved a few problems as well. And today we are going to continue with systems for which zeta is equal to 1. So now let's consider the next situation. And in our next situation, again, we are going to end our discussion today on this transient response of second order systems with overarching notes on the entire thing. And the second half of the class would be like on generalized discussion on second order systems, and the discussion that we will make would have long lasting impact on our entire course here. Okay, so be careful about that. Again, the first half would be like very difficult calculation for the most part. Okay, so now we are considering the situation where zeta is equal to 1. So this is known as a critically damped situation. So a critically damped case, this is critically damped. All right, so these are the names. Again, when zeta is equal to 0, we call it undamped, and that was evident from the response, because the response was never getting damped. It was a perpetually oscillatory response, right? Then when it was underdamped, the damping was there, but the effect wasn't that much that the oscillation wouldn't be visible. The oscillation would be visible to some extent depending on the damping ratio. Okay, so that was underdamped. Now we have critically damped. Okay, so now recall the system's transfer function we have been talking about was given by this. And now we have considered zeta to be equal to 1. So this term is equal to 1. So I'm not wasting any space. I'm just writing 2 omega ns, because zeta is equal to 1 under this consideration here. Under this particular consideration here. So we have chosen zeta to be equal to 1. So our damping ratio is now equal to 1. So that is one of the remaining cases. Now, of course, the other remaining case would be zeta greater than 1. And we are going to look through those as well. Alright. And as usual, if you have any query during the class, feel free to ask. Alright. So let's see. Of course, my input is once again the step input. So because we are calculating the step response, so that's 1 by s. So that's the step input, the Laplace transform of the step input rather. Okay, but before I go further, let's figure out the location of the poles here. So of course gs has this particular values, right? So this particular expression. So if I try to simplify the denominator, I would see that this is s square plus 2 omega ns plus omega n. That's a very nice form actually. So that is just s plus omega n whole square. Isn't that it? Right? So the pole locations are, poles are both at s equal to minus omega n, and again the other one is also at minus omega n. So if I draw my complex plane here, okay, my complex frequency plane, so this is the real part of s and this is the imaginary part of s. Okay, then my poles are located, for this particular scenario, both the poles are located at the same point, so they are real and equal poles. So we are saying they are real, they are no longer complex conjugate like the previous cases. They are real and equal poles, and both poles are at s equal to minus omega n, minus s equal to minus omega n. So these poles are real and equal, and they are on the real axis here, like that. Okay, so these are the pole locations. Fine. So what about the Laplace transform of the output? That would be, of course, product of the Laplace transform of the input with that of the transfer function. So with that said, the Laplace transform of the input is 1 by s, and gs is of course omega n square by s plus omega n square. So let's write that, omega n square divided by s plus omega n square. So that's the Laplace transform of the output. Now of course we want the output in the time domain, so we have to take a Laplace inverse on this, right? But before I can take Laplace inverse on this, I shall have to do partial fraction, because otherwise we don't readily have any formula to go with this one, right? So with that said, let's do partial fraction expansion. Now, of course, if I have expression of this form, the partial fraction expansion is a by s. Now, whenever I have a square term, whole square term of the variable here, then that is divided into partial fraction this way. So we would write b by s plus omega n plus c by s plus omega n whole square. So that's the standard way of expanding it as partial fractions. Now we are going to compare the partial fractions here. What? Someone has asked a question. Maybe there was some pun intended, but I did not get the pun somehow. What omega? I don't know. So if this is not a fun question, can you just ask it once again? Okay, so now if I, of course, I have to now compare these two terms, right? So in the numerator here, if I do the partial fraction here, do the addition here with the partial fraction, the numerator here would be a s plus omega n square plus bs into s plus omega n plus c. Yes, I'm absolutely sure this is going to be p omega n square, right? But the thing is, if I don't write p, or rather 2, 3, whatever, some number, some scaling factor, okay, right? All you have to do after doing the entire calculation, just multiply the result with p. So instead of this, if I have 3 here, after doing the calculation, I mean after calculating yt, okay, just multiply that with 3. Okay, that would be it. So the response would just be scaled up in the amplitude direction, right? This is just an amplitude scaling. That is why we are omitting that particular term here, that particular scalar multiple here, right? That particular gain term. Okay, that's called a gain term or a scalar multiple. Okay, so if I get rid of the scalar multiple, my calculation becomes easier. In turn, for you, what happens is that if you want the scalar multiple back, all you can do after doing the entire calculation, you can just bring that back by just putting the multiplying factor. So if I have 5 here, everything will be multiplied with 5. So that is not a difficult thing to understand, right? So if I have 5 here, so everything can be multiplied with 5 and so on, right? So the calculation will go on as usual, right? So you have to apply a little bit of brain here. All right. So again we have taken care of the numerator here. And what was the desired numerator? The desired numerator was just omega n square. Now these two are equal here, identical, sorry. These two are identical, right? And we are going to make use of this identity to figure out the value of a, b and c, right? That is the whole goal here. So with that said, so let's put a suitable value so that b and c gets vanished. So let's put s equal to 0. If I put s equal to 0, then this term vanishes, this term vanishes, this term vanishes. So I will be left with this. So this becomes a omega n square, and that will be equivalent to omega n square. So with that said, we have found a value for a, and which is going to be equal to 1. Now let's figure out another value for which some of these become 0. So let's put s equal to minus omega n. So if I write minus omega n, then this term becomes 0, right? Right? So if I put s equal to minus omega n, this term becomes 0. Also this term becomes 0. So I am left with this one. So this becomes c multiplied with minus omega n. So that is the value we chose for omega n. And on the right hand side, we have omega n square. So if I do the simplification, c becomes minus omega n. So that will be omega n square divided by minus omega n. That's the value of c. Now we have to find out the value of b. And we are going to do that by comparing the coefficients of s square on both sides. Now if I compare the coefficient of s square on both sides, here what is the coefficient of s square? That would be a, right? Here what is the coefficient of s square? That would be b. So what is the total coefficient of s square on both sides? If we just expand this, that's going to be a plus b, right? So a is the coefficient of s square contributed by this factor, b is the coefficient of s square contributed by this, and that has to be identical to the coefficient of s square on the right hand side. But what is the coefficient of s square on the right hand side? That's 0. So with that said, a plus b has to be equal to 0. So of course b has to be equal to minus a, and with that said, b will have to be equal to minus 1 because a is equal to 1. So we have just figured out the particular values of a, b and c, right? So we are going to put that here. Okay, so a was 1, so this is 1 by s. Okay, b was minus 1, so this is minus 1 by s plus omega n, and c was minus omega n, so this is minus omega n divided by s plus omega n. So that's ys, that's the Laplace transform, the output we have been looking for, right? So let's again copy and paste it here. So after doing the rough calculation, we just figured out that this was the Laplace transform of the output. Okay, now of course we are going to invert this, but before I jump into inverting this one, try to figure out something important here. Okay, so we know what is the inverse Laplace transform of 1 by s plus omega n, right? Because now again, time for rough work. We know that the Laplace transform of e to the power minus omega n t ut, that is 1 by s plus omega n, right? So that is useful here. So we have 1 by s plus omega n. So if I invert it, so that will become e to the power minus omega n t, right? But what about the Laplace transform of t e to the power minus omega n t ut? Of course, that was the original function. Now if I multiply that with t, then the Laplace transform, in the Laplace transform, we have to take a minus sign and the frequency derivative of the Laplace transform itself. So that was the frequency differentiation property, something we actually proved earlier. So if I just do that, so what is the derivative of this entire thing with respect to s? So that's gonna be s plus omega n whole square, and there is a minus sign already, and there will be a minus sign because of the derivative. So I would have this. So that's just the derivative. So we now found that this is the Laplace transform. So the Laplace transform of t e to the power minus omega n t ut, that's 1 by s plus omega n whole square. How is that important? We already have a term like that. All right, I think you got this, right? So with that said, let's write this as 1 by s minus, let's take the minus sign here, and we have 1 by s plus omega n, and let's put minus omega n into 1 by s plus omega n square, right? So now we can happily do the inverse Laplace transforms here. So therefore if I calculate the inverse Laplace transform, so that we have yt, so inverse Laplace transform of 1 by s would be ut minus inverse Laplace transform of 1 by s plus omega n, that's gonna be e to the power minus omega n t, of course with a ut, minus omega n is there, just the multiplication factor, and inverse Laplace transform of 1 by s plus omega n whole square would be t e to the power minus omega n t ut. We just figured this out moments ago. So that's going to be t e to the power minus omega n t ut. Notice very carefully that there is no oscillatory term anymore, right? So when the system is critically damped, there is no longer any sinusoidal term present in the response of the system. So we can take ut common out of this, so this becomes 1 minus, and I can also take e to the power minus omega n t, so that would become 1 plus omega n t e to the power minus omega n t, and that whole thing is with ut. So ut just indicates that the response is there for t greater than equal to 0, and when t is less than 0, the response is equal to 0. Now notice very carefully that there is no oscillatory term, so no sinusoidal term anymore, right? No sinusoidal term present anymore. Okay, and as such, if I draw the response here, if I draw the response with respect to time, so this is time and this is yt, and of course again you can calculate the final value of the response. Just put t tending to infinity. This will be 0 but this will be infinity. Okay, if I ask you what is the final value of the response here, what would you do? You can apply the final value theorem, but let's calculate the final value of the response here. Think about this term here. This is 1, right, when t tends to infinity. What about this term? That term can be written as, put some space here. Okay, let's just do this, right? So if I take the limit t tending to infinity, and we're trying to find out the limit on this, right? So that's 1 plus omega nt divided by e to the power omega nt, because that was e to the power minus omega nt. Okay, now if I take the limit, this is going to be 0. But the thing is, when t is infinity, this is infinity, this is also infinity. But this infinity in the denominator is a infinity of higher order, because if you look very carefully, the numerator is 1 plus omega nt. What about the denominator? What about e to the power omega nt? If you do a series expansion on this, you know this is going to be 1 plus omega nt plus omega n square t square by 2 factorial plus omega n cube t cube by 3 factorial plus omega n to the power 4 t to the power 4 by 4 factorial, and so on. So you can understand the polynomial in the denominator has higher order, higher power, much higher powers than the polynomial in the numerator. So if you put infinity, in a sense, the infinity in the numerator would have lower order than the infinity in the denominator. It's a bad way of saying this, okay, but let's divide everything by t. If I divide the numerator and the denominator by t, I would have 1 by t here. This t will cancel out. This t will cancel out. I would have just t here. I would have t square here. I would have t cube here. 1 power will get reduced. Now if I put the limits, limit t tending to infinity. Now if I put the limits, see, the numerator is a finite quantity. What about the denominator? This part is 0, okay, and this part is infinity plus infinity plus infinity. So I have 0 by infinity. So finite by infinity. So finite divided by infinity is 0. So this limit is equal to 0. All right. It's a very simple thing to understand, I think. All right. So with that said, let's calculate the response. Yes, you can use L'Hopital's rule. But we just did it from the first principles without using L'Hopital's rule or anything like that, right? So again, so this is yt, we are calculating the response, right? So the final value of the response is once again equal to 1. Once again, just one heads up, if I, instead of writing this, if I write p here, then of course all these will be multiplied by p, so subsequently this will also get multiplied by p. So the final value of the response will become p instead of being 1, right? Everything gets multiplied, right? Because Laplace transform is a linear operation, right? So all these things will get multiplied by p if I have p there, right? Everything will get multiplied by p. So that is something you have to remember. All right. So the final value will become p. So now here, at least for our case right now, the final value of the response is equal to 1. So that's the final value of response. So that's equal to 1, right? All right. And this is the response. So when time is less than 0, the response is 0, right? Now when time reaches infinity, the response is 1. So after a long time has elapsed, the response is equal to 1. And now the response here is a sum of 2 exponentials essentially, and one of the exponentials have a t multiplied with it. So if you do the calculations and draw it, I'm not going into the detailed calculation here, you would see that the response kind of looks like this. So there is no oscillatory term, so it will not overshoot it. There will be no oscillatory nature like the underdamped scenario, right? So this is called a critically damped response. So this response is for a critically damped system where zeta is exactly equal to 1, right? Now our previous definitions of rise time, peak time, settling time, etc. now will change for this. Of course, there is no peak here, so there is peak time is no longer defined. Okay, peak time will be no longer defined, and there is just one small mistake in the drawing. Let me just draw this correctly. Hold on for a second. Okay, so that is how the response actually looks like. There is some sort of flat response here. Okay, so this is for zeta equal to 1. All right. So now, of course, there is no peak time, right? If I ask what is the peak time, I mean, that should be infinity, really. The maximum value is reached when infinite time has elapsed, right? So there is no peak here, so there is no peak time. What about the rise time here? Now, of course, it does not reach the final value of the response for the first time. So that is how we defined rise time for this kind of systems, right? Now again, rise time is not defined in that way, but instead rise time is defined in an empirical way. What is the empirical way? I mean, this is like a very crude and rough way, for example. Okay, not a perfect way. So rise time will now be defined by the time taken by the response to reach from 10% of the final value to 90% of the final value. This is what I mean. The final value of the response is 1 here. If I multiply everything with p, the final value of the response will be p. So what is the 10% of the final value? So that is what the 10% of the final value is. So that's like 0.1. And what is 90% of the final value? Say this is the 90% of the final value of the response. That's like 0.9. So this is the point. This is the point in time. Okay, it reaches 10% of the final value of the response. Okay, and this is the time at which the response reaches 90% of the final value of the response, right? So this time gap, okay, this time gap is now empirically defined. This time gap, the time it takes to reach from 10% of the final value of the response to 90% of the final value of the response, is now known as the rise time. So now you can understand this is no longer analytical. I cannot just analytically calculate a very nice looking value like pi by beta by omega d and tell you that this is the rise time. No, this can only be done computationally. So you can use a computer to calculate the rise time now. You can no longer calculate the rise time like this and using that analytical method, because this is now an empirical definition. All right, there is no peak time. Peak time is not defined, no longer defined, right? Similarly, peak overshoot is no longer defined, because you can understand that the peak is reached when time is infinity, right? So those two terms are not defined. What about settling time? Settling time has the same definition as before. TS, the settling time, has the same definition. Same definition. So what is the definition? How much time it takes for the response to reach a 5% boundary or a 2% boundary about the final value of the response and never leave from there. But TS has the same definition here, but not the same formula. So you have the definition of TS, which is there for you, but the problem is that you can no longer use that old formula that we derived, like 3 by zeta omega n, and approximately calculate TS. That no longer works here. Okay, so definition is the same, but the formula is not the same. Okay, so again, everything when the value of zeta goes beyond 1 and equal to 1 and beyond 1, then all these formulas we derived will actually automatically break down. Okay, and again, TR has that different definition, and of course there is no formula for TR. Okay, so we have these two characteristics mostly, at least for this kind of systems, right? With that said, though, there is another characteristic. So two of the characteristics we figured out already are kind of no longer there, right? No longer there. So there is another characteristic which is there instead of these two standard characteristics. So let me just write down how can I do that? Let me just bring these lines down here. So that was the settling time, right? Sorry, rise time, right? Okay. So now there is another definition. Now let me use a different ink here, right? So when the system reaches 50% of the response, say this is the 50% line, right? So this is the 50% line. So that's like 0.5, 50% of the response. Okay, this is the amount of time it takes to reach the 50% of the response. Okay, so the time it takes to reach the 50% of the response starting from the beginning is known as the delay time. Now we have two different definitions. So let's write down rise time, time taken by the response to reach from 10% of the final value to 90% of the same of the final value. All right, that's the rise time. What is the delay time? So we have another definition, right? So two of the previous parameters are no longer there, peak time and peak overshoot. Now we have another time called the delay time. So this is known as the delay time. So delay time is the time taken by the response to reach 50% of the final value from the start. All right, so from the start, the time it takes to reach 50% of the final value is delay time. But you have to understand that all these definitions are empirical definitions. All these definitions are empirical definitions. None of these definitions are like analytical proper, okay, closed definitions like that. These are all empirical definitions, right? So you can do your numerical calculations and figure out these things, but you cannot have a proper formula representing everything. But you have to just keep this in mind. So that's a critically damped situation. All right. So we are now left with situations for which zeta is greater than 1, right? Again, if you have any query, feel free to ask. So now we are considering the last situation, zeta is greater than equal to 1, and this calculation is going to be pretty cumbersome. Okay, so please pay attention, I would say. Even if you don't pay attention, it's fine. Just try to understand how I derive the inverse Laplace transform in this particular scenario, because that will be important to understand. And off the top of my head, I cannot even tell you the formula. I can only derive it. So as with many things, I cannot tell you the formula of the top of my head, but I can derive those formula. So that is something you need to learn in this particular one. At least you cannot really remember the formula, or rather you wouldn't want to remember the formula for the response here. So this is called an overdamped situation, right? So again, if I write down GS, which is the transfer function of the system we have been dealing with, so that's s square plus 2 zeta omega ns plus omega n square. Yes, someone is asking, do we have third and higher order systems? Yes, we do absolutely have third and higher order systems, right? And we are going to look into those briefly. Okay, but rather I would say we are going to look into third and higher order systems later on. Okay, we would develop generalized methodology to analyze those, right? So the way we are tackling first order and second order systems is pure brute force mathematics, right? So we are just directly applying inverse Laplace transform and doing all the calculations. Those won't be suitable when we have even higher order systems, right? I mean, we cannot just brute force our way into this using inverse Laplace transforms, right? That would become infeasible. So we would have to develop more generalized techniques to handle those kind of systems. And don't worry, people did develop those techniques back in the 1950s, 1940s, right? Many of the engineers who developed these things, some of them were working on designing amplifiers. Some of them were working in the aviation companies, so aeroplanes, right? Aviation companies, and they really had systems like seventh order, eighth order systems. They had to design controllers for, right? So yes, they did develop everything. And the analytical methods that we are going to use, okay, would be you would see that those are designed in a way that those can be actually done without using a calculator, right? Because back in those days you didn't even have a computer, right? Let alone calculators. Okay, so we are going to look into those later on, don't worry. And we would kind of devise better techniques than pure Laplace transform and transfer functions and everything. Okay, for higher order systems, again, transfer functions essentially don't give you much of any information. Rather, things become more complicated if I use Laplace transforms. Okay, so we are going to avoid Laplace transform altogether later on. Okay, we're going to see those mathematical techniques. Okay, and again, all the techniques revolve around the idea that the calculation should be as simple as possible so that people can do it by hand. Okay, so that was the whole idea back in 1950s, to keep things as simple as possible. And when you cannot keep things simple enough, you had something called analog computers, and we are going to see how analog computers did work. Okay, analog computers essentially are bunch of op-amps, and we're going to see those later on. All right, so let's do a simplification here. Keep in mind that zeta is greater than 1 here. Okay, keep in mind zeta is greater than 1 here. So on the numerator I have omega n square, on the denominator I have s square plus 2 zeta omega n s. Now let's write zeta square omega n square. So this becomes a whole square, right? This becomes a whole square. So this is s plus zeta omega n whole square. So I have to subtract this zeta square omega n square, and we had omega n square. So that is the simplification that is the edit we did. So we added zeta square omega n square and subtracted zeta square omega n square. Fine. So on the numerator we have omega n square. Now this becomes s plus zeta omega n whole square. This entire term becomes s plus zeta omega n whole square. And what about these terms? So if I take a minus sign common out of this, I would have zeta square omega n square minus omega n square. Now look at this quantity very carefully. Zeta is greater than 1, right? Zeta is greater than 1. We chose this one, right? Since zeta is greater than 1, what about this quantity? This is a positive quantity. So this quantity is positive, right? Because zeta is greater than 1. So zeta square omega n square is going to be larger than omega n square. So this quantity is positive. So this is a positive quantity square, and this is another positive quantity. Just keep in mind. Okay. So now with that knowledge, let's just keep in mind that this is greater than 0. Right. So this is omega n square divided by s plus zeta omega n whole square minus, so let's write it down as zeta square minus 1. Now keep in mind that this is not a complex quantity anymore, because zeta is greater than 1. So zeta square minus 1 is a positive real number, and as such square root of that is also a real number, and we have omega n, let's put a whole square. That's fine, right? That's fine. So that's your GS, right? So now of course if I want to calculate the pole locations, I have to equate it to 0. So let's do one more line here. So this is like a square minus b square. right? So this becomes s plus zeta omega n plus root over zeta square minus 1 omega n and multiplied by s plus zeta omega n minus root over zeta square minus 1 omega n. All right, so that is the term we have, right? All right, so if I ask you what are the pole locations, right? So the poles are of course at s equal to so here either this term will have to become 0 or this term will have to become 0. So these are the poles, right? So zeta minus zeta omega n minus root over zeta square minus 1 times omega n, or so these are the pole locations, and s equal to, so all this term has to be 0, right? So that the denominator is 0, right? So this is equal to minus zeta omega n plus root over zeta square minus 1 omega n. All right, so these are the pole locations, of course, right? Now of course these are real poles. You can understand that these quantities are just real numbers, fixed real numbers, right? All right, so real numbers, particular real numbers, right? Now of course if I do the pole zero map here, now look very carefully. So that's again the s plane, and that will be the real part of s. This is the imaginary part of s. Okay, and if I draw the pole locations here, one pole would be somewhere like here, another pole would be somewhere like here. Okay, so one with the minus sign would be here, one with the plus sign in the middle would be somewhere like here, right? So these are the pole locations. Now of course these poles are real and unequal. So real poles and unequal, of course both negative, right? Because okay, fine, this is negative understandably, right? Because both of these quantities have a minus sign, and this is also negative understandably, because look very carefully that zeta omega n would be larger than root over zeta square minus 1 omega n, right? Because because this can be written as minus root over zeta square omega n and plus root over zeta square minus 1 omega n, right? So this term, this root over zeta square is going to be larger than root over zeta square minus 1. Okay, so this term, however large, this is going to be larger, so the negative part will be larger, so both of them is going to be negative, right? That's quite easily understandable, I think, right? So both of them are going to be negative, as long as omega n is positive, of course. So poles are real and unequal, right? So we have figured some things about the pole zero map. So that was our GS, right? Now here comes the problem. The problem is that the calculation will be too cumbersome. Okay, so that is GS. What is the input? Once again we are calculating the step response, so the input is 1 by s. So this is Laplace transform of the step input. All right, so of course then what is ys? Ys is once again xs times gs. So Laplace transform of the input multiplied with the Laplace transform of the transfer function, that will give you the Laplace transform of the output, and that's going to be 1 by s times this entire thing. Okay, you want cumbersome calculation? Here you have cumbersome calculation, right? That's ys, right? And before we can even do inverse Laplace transform, we have to do partial fractions. All right. So let's do a simplified calculation. Let's assume a few things so that our calculation is at least doable, right? Let's assume some things, right? So this is like 1 by, so I'm assuming this to be a and this to be b, right? And this to be omega n square. So I'm assuming this to be a, this to be b. So keep that in mind. I'm not writing. Let's write this. So that's my a, That's my B. So I'm assuming A to be this, B to be equal to this. With that said, we have just written a simplified form at least, so that actually we can actually deal with these things, right? All right. So now, of course, we have to do partial fraction expansion, and for that we are going to assume A. Are we using this ink? Let's standardize everything. All right. So let's make this A by S plus B by S plus A plus C by S plus C. Okay, S plus B, sorry. All right. And of course, if we just compare these terms, then we would have on the numerator here, we would have A times S plus A times S plus B, and plus B times S plus B, plus C times S plus A, and that's going to be equivalent to omega n squared, the numerator on the other side, right? All right. So now let's try to simplify this. So let's try to figure out the coefficients. Let's put S equal to 0. Again, this is an identity, so for every possible value of S, this is going to be true. All right. So if I put S equal to 0, this becomes 0, this becomes 0. I have A times B, and that is equivalent to omega n square. So I would have A equal to omega n squared divided by AB. And remember, this is A, this is B. Okay. All right. And what about this? What about this term? What about this term? I have to remove this term. Can I do that? Yes, I can put S equal to minus B. So let's put S equal to minus B. If I put S equal to minus A, this term gets removed. This term also gets removed. So I would have B times minus A plus B, and that's again going to be equivalent to omega n squared, and which gives me B equal to, so that's going to be A times A minus B. So that's going to be omega n squared divided by A times A minus B. So you just do the calculation here. So we have calculated A, we have calculated B. You can imagine how complicated the calculation automatically becomes, right? Because this is A and these are A and B. You have to do the calculation simplification here. Of course, if you have a particular value for zeta, this calculation becomes much easier, right? If you have a particular value of zeta and omega n, so you would have fixed numbers for A and B, right? That the calculation will automatically become easier. And if I put S equal to minus B, then this term vanishes, this term vanishes, this term vanishes. I would have C times minus B times minus B plus A, and that would be equivalent to omega n square, which is now equal to C is equal to omega n squared divided by B times B minus A. Got it. So we have got A, B, C, all these coefficients. We have figured those out. Yeah, happily figured those out, right? All right. So we were talking about ys, right? So therefore ys is going to be A divided by S. Now, of course, A is omega n squared divided by AB. Okay, so omega n squared divided by AB, but we can kind of sort of simplify that. Okay, so what is AB? If you multiply these two terms, you would see this becomes this is something like A plus B, and this is something like A minus B, sort of. Okay, or rather, let's say this is sort of like X plus Y, this is like X minus Y. So if you multiply that, then this becomes X square minus Y square. So zeta square omega n square minus this whole thing, right? Minus this whole thing. So zeta square omega n square minus zeta square omega n square plus omega n square. So you can verify that AB is essentially omega n square. Okay, so AB is essentially omega n square, and because of that, this capital A is going to be 1. And since AB is omega n square, I can also further simplify this these terms here. Okay, look very carefully. Since AB is omega n square, this is going to be omega n square divided by a square minus AB, which is equal to 1, right? Got it? This can also be simplified further. Like this is equal to omega n square divided by b square minus AB. Again, AB is equal to, sorry, omega n squared. This is going to be omega n square. Should I? Let's leave this, huh? That's going to be omega n square. Let's leave these calculations here. Okay. So AB can be written as just omega n square. We can do these calculations as we please. Right. So this is going to be A by S. Now what is A? A is equal to 1. So that's going to be 1 by S. Plus B by S plus A. What is B? This is the quantity. So B is omega n square divided by A times A minus B, and this is the constant. This whole thing is the constant, and this by S plus A. And we have C by, so that's gonna be omega n square divided by B minus A, right? S plus B. Remember these big values of A and B. Okay, we assume something for A and B. Where is it? Here we assume something for A and B, right? All right, so we have that. So with that said, what is the inverse Laplace transform? What is the actual response here? So that's the inverse Laplace transform of this quantity is going to be ut, plus then again these terms will remain, and of course this is going to be e to the power minus at ut. Remember, A was that big complicated quantity. Okay, and this is going to be omega n square divided by B times B minus A, and that's going to be e to the power minus bt. Okay, all in all, if I again you would see that one of these quantities is negative, one of these is positive as such. Okay, if you do the calculations, of course. Okay, you would see those calculations later on. I mean, the point being, the response is once again has exponential terms. So this is the decaying exponential. This is also a decaying exponential. This e to the power minus bt, this e to the power minus at. But there is no oscillatory term anymore. So once the value of zeta reaches 1 and goes beyond that, there will no longer be any oscillatory terms whatsoever, right? So we can take ut out of everything. So 1 plus, I would have omega n square by A times A minus B e to the power minus at, and plus omega n square divided by B times B minus A e to the power minus bt. I would encourage you to put the values A and B and do the calculations, do the proper big calculation here. Okay, I would encourage you to put the values of A and B and do the total calculation. Okay, all right. So essentially you would have minus signs, you will see. Okay, at least one minus sign will be there. Okay, so we have two exponentials and one this. Okay, again the final value of the response is going to be 1, right? So now if I plot this response, if I do plot this response, this time this is the amplitude response, and again the final value of the response is going to be equal to 1. And again in the transfer function, if I have some multiplication factor, then that will be the final value of the response, but in this case we have 1. Right? Now this is going to be the response. Now look very carefully. The response is 0 when time is less than 0, and after that so this is kind of looking like our typical critically damped system, right? And this will be like that if the response is if zeta is close to 1, like 1 point something, okay, the response will be like a critically damped system. But if the value of zeta increases even further, the response will become even more sluggish. Okay, the response will become even more sluggish. So something like this will be like the response. And if zeta value increases even further, the response will be even more sluggish. something like that. So say this is like zeta, say this is example, for example zeta is equal to 1.1, then this is for zeta equal to 1.3 or something like that. So this is equal to this is for zeta equal to 1.7 or something like that. So the response becomes sluggish. And again the characteristics are the same. Okay, we have rise time defined the same way. Okay, rise time defined the same way as critically damped system. Rise time will be defined as we did for zeta equal to 1. So the time it takes for the response to reach from 10% of the final value to 90% of the final value. We would have delay time defined the same way and defined as we did for zeta equal to 1, and we would have settling time exactly defined as we did for zeta equal to 1. So again you can understand that the definitions are the same, but we won't have any proper formula per se for this particular scenario. That is the end of our first part of the discussion, and I said I would take about 1 hour to discuss the first part, right? Alright, so that's the first part of our discussion here. Okay, for the second part of our discussion, let's go back to our, again if you have any query, just feel free to ask them right now. Okay, I'll be back in just a minute. Alright, so now let's have some, overall discussion here. Okay, I don't think any one of you have any question. So if you don't have any questions, fine. Let's have some overall discussions, right? So this is our complex plane. Okay, let me just take these. Right. So let's draw our complex plane here. So this is the frequency plane our. All right. This is our fantastic S plane. All right. All right. So this is S plane. S saying. Okay. This is S plane, and this is the real part of S. And things will be properly visible once I get rid of the grid. Okay, and this is the imaginary part of S. Real part of S is often represented by sigma, so we often call this the sigma axis, and the imaginary part of S is omega, so we call this the j omega axis. Okay, we have these names particularly for. All right. So you have noticed that for undamped systems, the poles would be on the j omega axis, right? The poles would be on the j omega axis, and the poles are complex conjugate pairs here, right? So poles would be on the j omega axis, and they are complex conjugate pairs. All right. So let's go back to that particular discussion so that we can actually write those without any hesitation here. So we are going to undamped systems. Yeah, we are here, right? So the locations of the poles are plus j omega n minus j omega n, right? So these are complex conjugate pole pairs. One of the poles are at plus j omega n and another is at minus j omega n. So they are complex conjugate pole pairs, but they are on the j omega axis, just like that. They are on the j omega axis, just like that. So let's do one thing so that actually you can see. Hold on. I think this is something. All right, now it works fine. So say here is one pole, and same here is another pole. So this is denoting an undamped system, right? Now of course this values, so this is plus j omega n and this would be minus j omega n. Okay, these values are actually denoting the undamped natural frequency of the response, right? So these values are actually denoting the undamped natural frequency of the response. So essentially, if we have an undamped system, then the poles would be on the j omega axis, and the value of the pole, that's magnitude of one of the poles, will denote the frequency at which the response oscillates perpetually without decaying, right? Something we already know. Now for underdamped systems, the frequency, what should I say, the pole pairs would be somewhere like here, right? Something like that. Again, complex conjugate pole pairs, so they will be equally apart from the real axis, right? So this is something like that. Okay, and we said that we derived on that particular scenario that and let me do one thing. Let me just copy the axis because I would need that. Hold on for a second. Is it about to copy? Right. For underdamped scenario, say we have something like this. We have a pole here. We have a pole here. So we have two poles, complex conjugate pole pairs here, right? So we said we already we know that. So we know that this value, this length, okay, rather let me just draw these. If these are the pole locations, then we know that this particular length is zeta omega n. So this particular length was zeta omega n, okay, and this height was omega d, okay, this height was omega d, something we already know, right? And we chose something like this. So if I draw a line from the origin, okay, then that length of the line would be zeta omega n whole square plus omega d whole square, right? So that line has a length of zeta omega n whole square plus omega d whole square. But so that's zeta square omega n square plus what is omega d? So root over zeta square minus 1 omega n. So omega d square would be zeta square omega n square, sorry, 1 minus zeta square omega n. So that's going to be omega n square minus zeta square omega n square. So that's going to be just omega n square, right? We did this calculation. So this length is going to be omega n square. So wherever the poles are for the underdamped situation, the poles will be omega n square. So square root of omega n square, right? Square root of omega n square, so that's omega n. So the distance of the poles from the origin would be always equal to omega n, no matter what. Remember that situation when we had poles on the j omega axis for the undamped situation, the distance was omega n. Now here for the undamped situation as well, so for the underdamped situation as well, the distance of the poles from the origin is still omega n, right? Previously for the undamped situation, we have had poles somewhere like here and somewhere like here, but the distance from the origin would still be omega n. Try to understand, because this pole would be at plus j omega n, this pole would be at minus j omega n. So distance from the origin is still going to be omega n, right? You understand that particularly, right? So with that knowledge, now let's go back and define what we defined earlier. So we said this angle is beta, right? We said this angle is beta. So if this angle is beta, then what is cosine beta? What is cos beta? Cos beta is base by hypotenuse. So this base, okay, this base divided by this hypotenuse, right? So this base is once again zeta omega n. So zeta omega n, okay, and divided by hypotenuse, right? What is the hypotenuse? Hypotenuse is omega n. So what is the value? So therefore we find that cosine beta is just the damping ratio. So we defined an angle here, and with that angle now we know that the cos of that angle defines the damping ratio, right? So this angle, say if this angle is between 0 degree and 90 degree, if this is 90 degree, then the damping ratio would be 0. If this is 0 degree, the damping ratio would be 1. This is what I mean. Let me just copy paste my axis once again. Say we have pole pairs here, say somewhere here. So 1, 2, 3, 4, 5, 6, 2, 4, 5. Right? We have pole pairs here. Now, if I want to calculate the damping ratio, all I need to do is to take one of the poles, draw this line, figure out this angle, and whatever this angle is, I need to calculate cosine beta, and I would calculate the damping ratio. So because cos beta is equal to the damping ratio, right? So we know that already, right? Fine. So that's the damping ratio. That's corresponding to the damping ratio. Now let's draw this line here as well, right? Now do tell me, if I extend this line here, okay, what is this line actually denoting? What is this line actually denoting? If I extend this line further like that, for where beta is, yeah, someone is saying how can zeta be greater than 1? We are only considering underdamped right now. Okay, we are drawing it for underdamped because this beta thing is defined for underdamped systems, right? We did not define it for overdamped or critically damped systems, right? We are just considering underdamped system right now, right? All right. So we have pole pairs like that. We have a particular value of zeta. Now forget these pole pairs in orange. Now say we have pole pairs like this. Now say we have pole pairs here and here, right? Here, these two poles. Okay, so we have a system where the poles are like this. Okay. I am not interested about the value of omega n just yet. Okay, now look at the green ones. Now if I calculate the value of beta, they will have the same value, and subsequently cos beta will be zeta, right? Try to understand where I'm going from this. If I have pole pairs here and here, of course they are complex conjugate pole pairs, right? They would always appear in pairs, right? If I have pole pairs here, this pink pair here, okay, for that as well the value of beta is the same, so zeta is the same, right? So we can have pole pairs anywhere along these lines, and they will denote systems with the same value of zeta. Do you understand my point? They will denote systems with the same value of zeta. So this this system with the red poles have a particular value of zeta. Okay, this system with the orange poles, if I have a system like that, they will have that same value of zeta. And for the system with the green ones, so poles located by the shown by the green poles here, they would also have the same value of zeta, because zeta is entirely determined by this angle. Okay, try to understand. The zeta is entirely being determined by these angles. All right. Okay. So this pair and this pair, and in our drawing at least this pair, they have the same value of zeta. Okay, because the angle they are making, these poles are making with the origin like that, the beta angle is the same and cosine beta is zeta, so they have the same damping ratio. So if I construct a system with these two poles or these two poles or these two poles, they would have the same damping ratio. I think I made this clear, right? They would have the same damping ratio, right? Let's take this a bit further. Let's take this a bit further, and I'm running out of ink, unfortunately. Let's use a different ink. Ink. All right. So let's draw another line here. Not that bad looking line. So essentially, if I draw a line like this, so the angle essentially determines the damping ratio, right? So if I draw a line like this, the angle, this angle here is essentially determining the damping ratio. So if the angle is close to this 90 degree, so this is close to 90 degree, then the damping ratio would be close to 0, because cos beta is 0, cos 90 degree is 0, right? Okay, and that's true because we saw that if the poles are on the j omega axis such that beta is 90 degree, damping ratio is 0, because those were undamped systems, right? So if I have poles on this line, which is now vertical on the j omega axis, that would be undamped because beta is now 90 degree, and since, so this is 0 degree, right? So this is 90 degree, so beta is 90 degree, and so if the poles are on the j omega axis, beta is going to be 90 degree, cosine beta is going to be 0, damping ratio is going to be 0, right? Got this? Fantastic. So if I have poles on this, damping ratio is going to be 0. Got it? Similarly, as we go on decreasing the angles, what happens? Cos beta increases, right? Cos 0 is 1, we know. So, and cos 90 is 0. Cos 0 is 1 and cos 90 is 0. So again, as we go on decreasing this beta angle, what happens? Damping ratio increases. Damping ratio increases. Understood, right? Damping ratio increases. And when I am here on this axis, so if the poles are on this axis, okay, the system could be critically damped, system could be over damped, right? If the poles are on this axis, the system on this axis, the system could be critically damped or over damped, depending on whether the poles are equal or separated, right? Equal or unequal, right? If the poles are equal and on this axis, on the real axis, then the system is critically damped, so zeta would be equal to 1. And when the poles are on this axis but they are different, so real but unequal poles, zeta is greater than 1, so over damped system. But for these parts, starting from damping ratio 0 and up to 1, not including 1, we have particular lines like this, right? Fantastic lines like that. So let's draw one set of line here. Nice line like that. Now any pole pair that lies on these lines, say I have a pole pair like this, so one lies here and of course one lies here. So this pole pair, they have a certain damping ratio, right? That is determined by this angle here. But once again, we have a certain angle here, right? So say this is another beta, another angle, right? So say this is another angle beta here, for example. So this has a certain damping ratio, right? This has a certain damping ratio. So now if we have, say, poles here, if we have poles here and here, these two pairs, they would have the same damping ratio. Unfortunately, I have to change the ink somehow. What can I choose? Let's choose red. All right, right? These two poles, they have the same damping ratio, because once again beta value is the same. Okay, choose another one. I think, can I choose? I'm running out of. Let's choose this white one, right? So I have, say, poles here, and here. So for this white pole pair also the same thing, since they are on this axis, they have the same damping ratio, right? So instead of drawing this, writing this way, I am now saying that these two lines are corresponding to a certain value of zeta. Say in this particular scenario, say this is denoting zeta equal to 0.3. Say this is zeta equal to 0.3. So this line is corresponding to zeta equal to 0.3. So what I mean is that if I have pole pairs on this line, on these two lines essentially, then the system that I would end up with will have the same value of zeta, namely 0.3. Similarly, say this is zeta equal to 0.6. Say zeta equal to 0.6. What I now mean is that if I have pole pairs that lies on these lines, will have the same damping ratio, 0.6. Alright, and just like that I can draw many of these lines, many of these lines. Say I can now draw this line, of course not like this, let's draw this line, and so now this is these white lines, they corresponding to another value of zeta, because they have a different value of beta, right? So they corresponding to another value of zeta. So if I have pole pairs on these white lines, they would have different values of zeta. Say they are corresponding to say they corresponding to zeta equal to 0.1. So if I have pole pairs on this, so then zeta will be equal to 0.1, right? Try to ask any questions you might have. All right. So of course, which one is left? Of course, the vertical line is left. So this vertical line, if I draw a vertical line, just as I told you moments ago, that this is the line we are drawing, right? So this line corresponds to different values of beta and subsequently different values of the damping ratio. So if I draw a line like this on the axis itself, okay, on the j omega axis, that is of course corresponding to zeta equal to 0, because for this angle, this line, beta is equal to 90 degree, right? So this is denoting zeta equal to 0. So zeta equal to 0 for this, because for this beta is equal to 90 degree, right? Just like that. I think you got this, right? Any confusion with this? Okay. So if I am comparing two systems and they have pole pairs which are on the same line from the origin, they would have the same damping ratio. Right? And of course, with that said, of course we would have to draw one more line, okay, namely this one. Of course, this line, so this is zero damping ratio, right? Damping ratio increases as beta decreases. Damping ratio increases, and this line, when this is on the real axis, when this line is on the real axis like that, when this line is on the real axis, this is zeta greater than or equal to 1, right? Depending on how the poles are located. If the poles have the same value, then zeta would be equal to 1. If the poles are having different values, then zeta would be greater than 1. So we are saying zeta greater than equal to 1 on this line. With that said, what I have done, we have drawn a certain grid on the j omega axis. So we have drawn a certain grid on the j omega axis, that denotes lines depicting constant damping ratios. So if there are pole pairs on any of these lines, okay, they would have the same damping ratio, right? Okay. Any confusion, please let me know. So essentially, if I want to describe this, I would say uh, pole pairs, of course pairs, right? I have two poles, second order systems, right? Pole pairs on any of on a certain line pair, four pole pairs with the same value of beta will, I know my head is blocking this, will have the same value of zeta. Pole pairs with the same value of beta will have the same value of zeta. Got it? So if the poles are on the j omega axis, okay, it's an undamped situation, right? So we figured out if poles are on the j omega axis. So what is j omega axis? Of course, this vertical axis, right? Poles are on the j omega axis. So let's write down, draw a few examples. So if I have poles here and here, they are denoting zeta equal to 0. If I have poles here and here, those are all zeta equal to 0, right? So if the poles are on the j omega axis, it denotes zeta equal to 0. So undamped system, right? So if poles are complex conjugate pairs, poles are complex conjugate pairs and are on the left half plane. Now what is left half plane? Left half plane is of course the left half of the j omega axis. So pole with negative real parts. So right, so we are not drawing poles anywhere here, right? This part is known as the left half plane. Why are we not drawing poles on this part? We will later on see that if poles are on this part, the system is unstable. We would see why. Okay, and then if the poles are complex conjugate pairs and are on the left half plane, let me just write it down, left half plane. So in short, it's called LHP. Then it denotes zeta is between 0 and 1. Okay, so essentially depending on which line they are on, so depending on the value of beta, it will determine the damping ratio. All right, so this is underdamped. So all these lines are denoting underdamping, right? All these lines denoting underdamping. So poles anywhere here would be denoting underdamped systems. So poles on the j omega axis would denote undamped systems, right? Similarly, previously we just moments ago figured out if poles are real and equal, and are on the left half plane. So essentially the critically damped situation. So if the poles are real, equal, and are on the left half plane, then of course zeta is equal to 1. So this is called a critical damping. So it's critically damped. Okay, and we also figured out if poles are real, unequal, again English lesson, equal, equality, unequal, inequality. if poles are real, unequal, and are on the left half plane, then zeta is greater than 1. So this is called overdamped. So these are the all possible dampings that you could have. You can have negative damping, and again negative damping would denote unstable systems. So we are not going to discuss that. Okay. So just keep these in mind. Any questions you have, ask right now. Okay. Just keep this in mind. All right. All right. Now we have talked about lines denoting constant damping ratios. Now we are going to denote something like lines for constant omega n, constant undamped natural frequency. Let's see what I mean. Okay, so we shall have to go back. We shall have to go back to the same discussion we had earlier. Okay. This was the undamped system, and for this undamped system, the poles were on the j omega axis, fine, and the distance, the poles were the distance of the poles from the origin was denoting the undamped natural frequency. So how far away the poles are from the origin at the undamped natural frequency. So omega n has this value, right? The direct distance here. Similarly, for the underdamped system as well, the distance, the direct distance here. So we, okay, the radial distance from the origin, that denoted the undamped natural frequency. So how far away the poles are from the origin, that determines the undamped natural frequency. Yes, how far away the poles are from the origin determines the undamped natural frequency. So let me again illustrate this properly. So how far away from the poles are from the origin denotes the undamped natural frequency, like that, right? So what if I want to draw all the points, okay, that have the same distance from the origin? Okay, so if I want to draw all the points, hold on, let me just take care of this. Let me take a new page. Don't mess anything up. I hope so. If I do, I will take care of it. Hold on for a second. All right. So now on this I want to draw all the locus of all the points that have the same omega n. So omega n is determined by the distance of the poles from the origin, right? So if I want to see all the points that are same distance apart from the origin, what would the locus look like? It would be a circle, right? It would be a circle. So let's draw a circle. Nice. Bring it here. Now it's going to be a very difficult drawing for me, so I would strongly suggest that you be patient. I just messed this up. Right. So it's a very small circle, right? But the thing is, any point that is on this circle, okay, will be the same distance apart from the origin, right? So any point you take on this circle will be the same distance apart from the origin. So if you have pole pairs anywhere on this circle, it will have the same value of omega n. Let me draw another circle. Again, I am trying my best to be a good artist here. All right. Okay. That's another circle. And any point on this circle will have the same distance from the origin. So if I have pole pairs on anywhere on this circle, they would have the same value of omega n. Got it? Let me draw another circle then. I made a mistake. Okay, let me just draw a circle from this guy. Circle. Take circle. Okay, I will take care of that. So this is what happens when you cannot draw, but you still try to draw. Nice. Okay. That's another circle. And this circle again denotes points from the origin that are same distance apart. Okay. Let's draw one more circle. Bring this here. This is going to be the last one, I promise. All right. Nice. Let's get rid of the page. All right. So what are these lines denoting essentially? So these lines are essentially denoting lines that have curves that have the constant value of omega n. So if we have pole pairs here, say omega n would be equal to 4. If we have pole pairs here on this curve, omega n would be equal to something like 3. Okay. So if I have if I have pole pairs on this, omega n is going to be equal to 2. If I have pole pairs here, say omega n is going to be equal to 1. So if I have pole pairs like that, and let me just do one thing. Let me just copy paste the drawing, because I would need this shortly. Nice copy. All right. So if I have pole pairs here, they would have the undamped natural frequency of 4 radian per second. If I have pole pairs here, they would have the same undamped natural frequency of 4 radian per second. If I have pole pairs here, they would have the same undamped natural frequency. What is different about them? They have different damping ratios, because if you draw a line like that from the origin, their beta value will be different, right? Similarly, this pole pair and this pole pair, with different ink, this pole pair and this pole pair, this pole pair and this pole pair, they have the same undamped natural frequency, but their damping ratio are different. Because how do you calculate the damping ratio? You just draw a line and calculate the beta and this. So since beta is different, okay, they have different damping ratios, right? And again, this do not have to be integers, right? I mean, you can have pole pairs here and here. Okay, and of course the undamped natural frequency would be somewhere between 0 and 2, right? Of course, I have drawn integer lines because I like integers, right? Something like that. So this, so in words I can say, okay, rather distance of pole pairs from the origin determines the undamped natural frequency, the omega n. Okay, and determines the undamped natural frequency. So I think this is pretty easily understood without any confusion whatsoever, right? So this drawing here is called this drawing here. Okay, the problem is I do not have any place to put the caption on this drawing. This is called the constant damping ratio locus. So constant zeta locus. Since there are multiple locus, we have loci. Okay, so this drawing, this graph template is known as the constant damping ratio loci. Okay, plural of locus is loci. Okay, and this drawing is the constant undamped natural frequency loci. Okay, got it? Of course, the discussion that we are doing so far, the topic is, after this, the topic is, let's write down the topic here. The topic of discussion here, constant zeta and omega n plus I. So that is the point of discussion here. All right, that's the name of the topic. Okay. Now, what if I want to combine these two drawings? Of course, I can do that. So let's again change this. What did I do? Right. Yeah. Thankfully, I copied one thing, right? And this is why we copy and paste. Okay. So if I have pole pairs on this on anywhere on these circles, okay, they would have the same undamped natural frequency, right? And we also, along with that knowledge, we have this knowledge, this particular knowledge, that if I draw these lines, right, the angle with the negative j omega x, negative real axis, determines the damping ratio. So if I draw this line, yeah, sure. If I draw this line, let's start with the j omega axis, right? So now let's draw the constant damping ratio loci, right? So pole pairs on this would have 0 damping ratio. Okay, different ink. Pole pairs on this. Of course, we would have more circles actually. Okay, the number of circles are kind of small, whatever we have chosen, at least for what we have chosen, right? Anyway, it doesn't matter really. You understand the point, right? These lines are just there as grids, right? Poles can be in between any of these. Okay, let's use a different ink. Let's use this. I'm making sure that the drawing is consistent at least. And don't worry, drawing is one of the integral parts of engineering. You have to be able to represent what you have done. Okay, that's one integral part of engineering. All right. So that's theta. Again, same problem I'm facing. I'm running out of inks, different inks. Let's use whatever. As long as you people understand, it's fine, right? I think I made a mistake in previous one. That is what I'm saying. Be patient while I draw, while I try my best to draw at least. I'm really, really good at drawing, right? Nice. One more. So we have this. All done. It's done. Right? So these lines now actually denote constant damping ratio loci. Right? So now on the same graph, we can figure something very interesting out. Let's say, so this is denoting zeta equal to say 0.1. Okay. Do I even have places? So zeta equal to 0.1. So this is zeta equal to 0, right? Again, zeta equal to 0. So this is zeta equal to 0.1. So this is zeta equal to 0.1. This is zeta equal to 0. Say 2. This is zeta equal to 0.2. So again, these are arbitrary. Okay, so zeta values would actually depend on the angle, right? Zeta values would actually depend on the angle. Okay, you already understand that. So say this is zeta equal to 0.3. This is zeta equal to 0.3. Okay, this is say zeta equal to 0.5. Say zeta equal to 0. This is zeta equal to 0.7. Zeta equal to 0.7. And this red one is denoting zeta greater than equal to 1. So yes. So this grid, okay, the way we have drawn the grid is known as something called the S grid. Of course, S-plane grid. That is why this grid is known as the S-plane S grid. This has a particular name. This is known as the S grid. So S grid actually denotes as the constant zeta and constant omega n loci in them, right? So that is constant omega n. So that was constant omega n loci. Was constant omega n. Right. All right. All right. So as you can understand that these lines are already only crossing them at one particular point, one particular set of points, right? So there is only one single pole pair that has the same particular omega n, same particular uh, zeta, right? So let's copy this once more. I don't know whether I would be able to copy this. Right? We have that particular loci, right? So now say we have say we have pole pairs here. So we have pole pairs here. So if we have pole pairs here, then it is denoting a system that has an undamped natural frequency of 3 radian per second and a damping ratio of 0.3, right? Now if I need to increase the damping ratio, without changing the value of undamped natural frequency, what am I going to do? I would try to bring the poles like here, right? So I would maybe try to bring the poles here and here. Okay, so that way what will happen? The value of the damping ratio will increase without any changes on the value of the undamped natural frequency, right? So you can say this will increase. So this drawing here in this particular one. So what is happening? So we are increasing. So we increase zeta, keeping omega n constant, right? And of course, if I move along this, then I would decrease the value of zeta, keeping omega n constants, right? Omega n constant. All right. And also, say I have pole pairs here. Say I have a pole pair here and here, right? If I have pole pairs here, so now this system with the green, with these two poles denoted with green, okay, drawn with green. So this system has a damping ratio of 0.2 and an undamped natural frequency of 3 radian per second. If I want to change the undamped natural frequency, maybe increase it without changing the damping ratio, what I would do, I would pull the poles along this. I would try to pull the poles somewhere here. So now the damping ratio has increased. So damping ratio has remained the same, but the undamped natural frequency has increased, right? So this discussion is changing, rather increase omega n, keeping zeta constant. Yeah, things like that, right? So you understand these discussions. I hope so. All right. So now it's time for some rapid fire quiz for you. Okay. So this is S-plane. Okay. I'm not going to write sigma j omega every time, but I am going to randomly draw something and ask you a question. Okay. So, and your goal would be to answer the questions. So this is question number 1. My question is, so this is question number 1. Question is, so, and you would write down the answers with question number. Okay. Question is, I'm asking for the zeta value. What is the zeta value? For the second question, of course, there will be a slight delay between when I say something here and when you see something here. Again, the question is, what is the zeta value? Question number 3. Just write down whatever comes in your mind. Now, here I am denoting two systems. I am running out of pages. Again, be quick and answer your questions. I have two systems. So these are two systems. Question is, for this one, the question is, which one has higher value of zeta? Higher value of zeta. So answer either in say pink or green. Question number 3. Please answer the questions. Okay. Question number 4. Yeah, question number 2. One of your answers is correct. What about question number 1? And then let's draw it on a set. That's a system, and that is denoting another system. So we are only talking about second order systems. So pole pairs drawn with different inks are different systems. Yeah. So far whatever answers I have received are correct. Others, please try at least. Try at least. Okay. Here question is. What is same for the two systems? I mean, here for this one question is what is same for this orange system and the pink system? What are same? Question number 1 is yes. Someone is saying for the first one the answer is zeta less than 1. That is not just sufficient. You have to say zeta is greater than 0, less than 1. Okay, so what is same for this one? Damping ratio or omega n? Question number 5. Yes, all of you have got that. This fine. You have poles here, you have poles here. The question is, here the question is, what is zeta? So calculate the value of zeta for this one. This is question number 5, right? Yeah, for the first question, many of you have answered. The answer would be between 0 and 1. You have to say 0 less than zeta less than 1. Okay. For this one, you already have answered the questions. So for this one, the answer is 0, right? So what is the value of zeta for question number 5? Question number 6. So we have two poles at the same point. Question is the same. What is the value of zeta? Rather, so someone is saying for question number 1, question number 5, no, this is not. This is incorrect. So someone is saying for question number 5, zeta is equal to 1. No, it is not. For question number 7, here is one system, and here is one system. Question is like previous. What is same for these two systems? Many people are saying for question number 5, zeta is equal to 1. No. You people are pretty wrong. So these are the questions. So let's answer the questions. Okay. So for this system, zeta is between 1 and 0. So that's the correct answer. Between 0 and 1. For this one, zeta is equal to 0. Now try to figure out the answers that you have seen. And some people don't even try to answer the questions. Okay. So which one has the higher value of zeta? Of course, you can draw these lines and you can see this has a higher value of beta, so it will be having a smaller value of zeta, right? This beta is smaller, right? So of course higher damping ratio. So answer would be green, right? All right. So what is same for these two systems? So if you roughly draw a line from the origin, you would see that they are lying on the same line. So what is the same for these systems? Of course, what is same? Of course, zeta is same, right? For this particular system, the poles are real but unequal. So zeta is greater than 1. Question number 7. Question number 6. For this system, poles are real but equal. So this is a critically damped system. So zeta is equal to 1. Now, of course, for this system, what is the same? Okay, I did make a poor drawing, but you can understand the point here. Okay, if you draw a circle, which I am trying my best to do right now. If you draw a circle, yeah, they would be roughly on the circle. Okay, so roughly like that. So something like that. So what is the same for this system? Again, answer is omega n. Right. So we had a rapid fire round, and some of you figured out a few things, some of you couldn't figure out anything. Very nice. All right. All right. So that would be kind of the end of today's discussion, but I would leave you with a question. Okay. What if I draw a line here? What if I draw a line here? Okay. What kind of damping ratio would that tell me? Would that have? Okay. What kind of damping ratio would that have? So I would leave you with a question, and we are going to elaborate everything on that. Yeah, you do have to imagine the circle for the question number 7. Okay. So let's go back with this. Okay. So now this is again sigma. This is j omega. I think I skipped j omega in one. This is j omega axis, right? All right. So now say we know the damping ratio lines, right? Something like that. So now say I am drawing a constant damping ratio line. Again, these are all line pairs, right? And of course, for this one, say beta is 120 degrees. Beta is 120 degrees, right? Beta is 120 degrees. So that is understandable, I think. Yeah, very funny, right? So now question is, say we have a pole pair here and here. I haven't told you anything, right? We have a pole pair here and here. All right. So question is, uh, what would be the damping ratio of the right? So we have pole pairs here, complex conjugate pole pairs, and beta is something like 120 degree here. Okay, so it's a very simple question, and I would suggest you figure out what is the damping ratio, what the damping ratio is. All right, we are going to figure out things later on. Someone is saying these are unstable poles, right? Yes, these are unstable poles, and we are going to explain this. Actually, I found a very elegant way of explaining this. Okay, so if I am teaching signals and systems, and if I want to discuss instability, again, English lesson, unstable, instability. Okay, unstable, instability, equal, equality, unequal, inequality. unstable, instability. Okay, so English anyway. So the thing is, I actually figured out quite a few different ways of discussing stability in mathematical terms, right? So if I'm teaching signals and systems, there would be one particular way in which I discuss stability. If I'm teaching digital signal processing, there would be another way of discussing stability. If I'm teaching control systems, that would have another way of discussing stability. And if I'm teaching mathematics, of course, control theory is considered to be a branch of mathematics. In that case, stability will be discussed in yet another way. So we have plenty of ways of discussing stability. But for this one, just try to figure out what the damping ratio would be. Okay. And in that said, with that said, you would, let me give you a hint. If I had drawn lines on this one, on the right hand side, you would see that damping ratios would be negative. All negative damping ratios would be here. Okay, so just figure those out. Okay, so that would be the end of today's discussion here. So we kind of had generalized ideas on this. Okay, and again, we are going to take these ideas further. And whenever you are drawing something on the S plane, okay, at least using the control system libraries, okay, you would see that the S grid, is drawn automatically for you. This S grid thing, okay, would be drawn automatically for you, so that you can have ideas on what damping ratios you are dealing with, what undamped natural frequencies you are dealing with. Okay, so this is again a design tool. Okay. All right. So if you have any query, feel free to ask. Otherwise, we're going to end the discussion today. The thumbnail of today's class actually has this in it. Some version of this in it, right? All right. So if you have any query, feel free to ask. Otherwise, we're going to end our discussion today. Thank you very much for being patiently going through all these. And tomorrow in Control System Lab, we are going to design something. We are going to see in practice how, as an engineer, with whatever knowledge we have gathered so far, okay, we haven't gathered any design knowledge per se. We have only learned how to analyze in terms of time response and everything, right? Time response and all. Okay, and these damping ratios and undamped natural frequencies. With that knowledge, we are going to see tomorrow how, as an engineer, we are going to apply our knowledge to figure some things out, okay, about systems. Okay, so it is not just sufficient to write down and getting a plot and end of it. That's not it, right? So you practically need to figure out things as you go on. Okay. So we are going to have a lesson on that tomorrow. With that said, this is the end of today's discussion. Thank you for being here, and if you have any query, just drop me an email. Again, this handouts will be given to you. All right, so thank you very much. I will see you tomorrow.